Hello friends, welcome back to Be Pharmawise. In the previous video, we discussed the titration curve for precipitation titrations. In this video, we are going to talk about the methods of endpoint detection in precipitation titrations. This point is very important from your exam point of view. For 10 marks, this question will be definitely asked. Now, what we are going to discuss in this? So, we will be actually looking at the ways by which we can know that the end point is reached. So there are multiple methods. We will discuss them one by one. To enlist them, the first one is Mohr's method, second one is Volhard's method, next one is Fajan's method, and then we will discuss a method which is not much commonly used today, but it is there. It is Gay Lussac's method, which is also known as without indicator method. So let's now discuss one by one what these methods are, how they are going to work, and how they are going to tell us that how we are going to actually see that the endpoint is reached. So let's start from Mohr's method of endpoint detection. Now in Mohr's method, it is also referred as a direct method of titration. So when we are saying that it is a direct method, what we mean is our analyte is going to be the halide ion. So let's take an example of titration of say 0.1 molar NaCl solution with 0.1 molar silver nitrate solution. Now NaCl means it is a halide ion solution which is our analyte, and silver nitrate means it is silver ions solution which is our titrant. So as we have discussed in the earlier video also, when we are using silver nitrate as our titrant, the titrations are referred as argentometric titrations. Now this kind of titration where halide ion is our analyte, silver nitrate is our titrant, and we are going to use a particular indicator. In this case, we will be using dilute potassium chromate solution as our indicator. So see here, chromate ions will be behaving as an indicator in this case. So this is an example of a direct titration, and the method is referred as Mohr's method. Now let's look at the reactions going on. So what will happen is NaCl is our analyte. So this NaCl means the analyte ion, chloride ion, will react with the precipitating ion to form AgCl PPT. Right? Now once all the chloride ions are finished from the conical flask, what will happen is when the excess drop of silver nitrate will come down, now there are no more chloride ions. So it will react with the chromate ions. So now when Ag plus ions react with chromate ions, they are going to form the PPT of silver chromate, and the silver chromate PPT is reddish brown in color. So ultimately we are going to see a PPT which is colored at the end point of titration, and at that point we will close the knob of the burette, because we know that when the reddish brown colored PPT is being formed means all the analyte is reacted and the excess drop of silver nitrate is now reacting with this chromate ions, indicator ions, to give us colored PPT. So here we can state the underlying principle as formation of colored precipitate at the end point. Now what are the conditions we need to take into consideration? First, this titration has to be carried out in neutral to slightly basic pH. So it is very important that we maintain the pH in the level of 7 to 10. Now why this is important? Because if we go below 7, means if the pH is less than 7, means the solution is acidic. In that case, these acidic means there will be H plus ions present, and these chromate ions, they will immediately react with the H plus ions to form chromic acid. Now they are no more available to act as an indicator. So acidic medium we have to avoid. Now if the pH is more than 10, then also there will be a lot of OH minus, means hydroxide ions present in the basic medium, and those may react with our precipitating ion, silver ion, to form silver hydroxide PPT. So the precipitating ion which was supposed to react with the analyte ion, chloride ion, instead of reacting with this, it is busy reacting with the hydroxide ions and forming the silver hydroxide PPT. So both these cases are not beneficial. So we have to take care that the condition is neutral to slightly basic. How we can do this? We can use a solution of sodium bicarbonate or borax, which will help us to maintain the pH in the required range of 7 to 10. Now we can easily carry out the titrations of chloride and bromide using Mohr's method. But what in case of iodide? See, if I use a solution of iodide ion here, the PPT I am going to get is AgI, means silver iodide, and then at the end point I will have silver chromate PPT, right? The silver iodide PPT is also yellow colored and silver chromate is also reddish brown, so yellowish shade. So it is not offering a clear contrast. So I cannot identify that my end point is reached, where in this case I can easily see. So we are going to avoid titrating iodide ions with Mohr's method. For chlorides and bromides, it is a very suitable method. Direct titration, very easy to perform and gives you satisfactory endpoints. So this is the Mohr's method. Now we will talk about Volhard's method. Basically, Volhard's method is indirect or back titration method. So what do I mean by that? Suppose let us take the same example. My analyte is sodium chloride solution and my titrant is silver nitrate solution. Okay. Generally in direct titrations, we take analyte in the conical flask and our titrant in the burette. But in case of indirect or back titration, what we are going to do is we will place excess of titrant in the conical flask itself. So I will tell you what we are going to do. I will be taking NaCl solution, which is my analyte, and I will be adding excess of AgNO3 in the conical flask itself. Now what will happen? The sodium chloride will react with the AgNO3 in the conical flask itself, and the reaction will be somewhat like this. NaCl reacts with AgNO3 to give me AgCl PPT, right? Now once all the chloride ions are reacted with AgNO3, as the silver nitrate is in excess, some amount will be remaining in the conical flask. This remaining silver nitrate we are going to titrate using thiocyanate ions. So either use potassium thiocyanate or ammonium thiocyanate solution as your titrant, and this will react with remaining AgNO3. So how the reaction will take place? This remaining AgNO3 after complete reaction with analyte, remaining AgNO3 now reacts with thiocyanate solution to give me silver thiocyanate PPT. Now this silver thiocyanate PPT is also reddish brown in color. So at the first point I am going to get a colored PPT, but now how I will come to know that the reaction is over, all the remaining silver nitrate is finished, is reacted with the thiocyanate. So I have to use an indicator. So which indicator I will be using? I will be using ferric ions. So in the form of ferric nitrate or ferric ammonium sulfate. So ferric ions Fe+3, they'll act as indicator, and what will happen is once all the remaining silver nitrate is also completely reacted, the excess drop of thiocyanate will now react with the indicator ion to form a complex ion like this, ferric thiocyanate +2. So this complex which is formed is a soluble complex, and it gives the solution reddish color, reddish brown color. Now reddish brown color is imparted to the entire solution. It is not that we are seeing formation of colored PPT. It is the entire solution is getting colored in the reddish brown shade. So by that I will come to know that okay, now the entire content in the conical flask is finished and my titrant, in this case thiocyanate ions, are now reacting with the indicator ion. So I will stop the knob of the burette and I will come to know that okay, the end point is reached. So this is how we are going to detect the end point by Volhard's method. Now it is very essential to discuss a few points related to this. Now in Volhard's method, as we said in the Mohr's method, the reaction is carried out in neutral to slightly basic medium. But in case of Volhard's method, the reaction is carried out in acidic medium. And how we are going to achieve it? We will be adding free nitric acid during the titration, which will maintain my levels in the acidic level. Now I can easily carry out the reactions of chloride, bromide, iodides as well as thiocyanates using the Volhard's method. Now but there is a limitation which we have to mention here. See, what happens is, now you know the sequence of events. First, my analyte has to react with the silver nitrate. Once all the analyte is reacted, silver nitrate which is remaining reacts with thiocyanate. And then once all the remaining silver nitrate is finished, the thiocyanate is supposed to react with the indicator. Now the problem here is the thiocyanate which falls down after the reaction of silver thiocyanate formation, which is supposed to react with indicator ions, might react with the AgCl PPT present over here. Now this AgCl PPT is already formed in the first step. After the second step, instead of going to react with indicator ions, the thiocyanate ions prefer to react with the AgCl PPT to form silver thiocyanate and chloride ions are set free. Now what will happen? When my thiocyanate was supposed to give the color, the end point, and I was supposed to close the knob of the burette, instead of reacting with the indicator, it is reacting with someone else. So it gives me higher reading than the actual reading, means a titration error is introduced. And now I have to remove this error, otherwise the entire titration is failed. So what I can do is, first I will completely react the analyte with my silver nitrate, excess of silver nitrate. Once the silver nitrate precipitation is complete, I will boil the solution for 2 to 3 minutes. Now why it is essential? Because silver chloride PPT is example of colloidal PPT. Now colloidal PPT has a particular tendency to adsorb its own ions which are in excess. Now whenever there is the titration going on, there are excess of AgNO3 present. So Ag plus ions are lying around in excess. So this AgCl PPT adsorbs the Ag plus ions and they in turn adsorb the oppositely charged ion. This layer is called as primary adsorption layer, and another layer which it will adsorb, a negatively charged layer, it will be called as a secondary adsorption layer. So this AgCl PPT is already it has been adsorbed the silver ions. So first I want to dissolve them. So I will boil the solution. Once I boil the solution, what will happen is these Ag plus ions will be dissolved and AgCl PPT will be freed. After boiling, when all the desorption has been occurred, I will filter the solution. Now after filtration, AgCl PPT will be removed from the solution. Now I will cool the solution and I will continue the titration, continue the back titration. The remaining amount of AgNO3 which is there in the solution will now react with thiocyanate, and as there is no silver chloride PPT present because it has been removed through filtration, the thiocyanate will now ultimately react with the indicator ion because it doesn't have the AgCl PPT to react with. So this is one way by which we can carry out the titration. But it is a tedious task, right? It increases the steps in the titration. So are there any more feasible ways? Then yes, what we can do is we can add a coagulant. So a coagulant like potassium nitrate can be added with the solution itself. Now when a coagulant is added, what it does is it actually prevents the adsorption of silver ions on the AgCl PPT. The coagulant reacts with AgCl PPT and makes it immobile. So now the AgCl PPT, first place, it does not adsorb any silver ions, and secondly, as it is in combination with the coagulant, it is now not available for the reaction with thiocyanate ions. So once it is formed, it gets engaged with the coagulant and hence it is actually protected from this side reaction, unwanted reaction. So this is another way. Third way what we can do is, instead of the coagulant, we can add some immiscible liquid like nitrobenzene, which will coat the silver chloride PPT. Now once it is coated with an immiscible liquid, it is again protected and hence it cannot react with the thiocyanate ions and give this unwanted reaction. So just by incorporating a coagulant or an immiscible liquid like nitrobenzene, we can actually achieve the same result which we can achieve through filtration. But as filtration is a slightly tedious process, we can opt for these two methods where we are using coagulant or the immiscible liquid. So this is a slight modification in the Volhard's method where we can achieve the same endpoint in single step without the need of filtration. This is referred as modified Volhard's method. So this is how we are going to carry out the endpoint detection by Volhard's method. So this method is actually very effective for titrating all kind of halide ions. The problem with iodides in the Mohr's method is also overcome, and with slight modifications we can overcome the inherent problems in the Volhard's method itself. So it is a good method to consider for detection of endpoint in precipitation titration. Now next very important point which can be asked for 2 marks is differences between Mohr's method and Volhard's method. So we will discuss the differences between Mohr's method and Volhard's method. Now talking about the differences of Mohr's method and Volhard's method, the first and obvious difference is Mohr's method is a direct method of titration, whereas Volhard's method is indirect method, or you can say back titration method. In Mohr's method, what is our analyte? Halide ions are our analyte and silver nitrate is our titrant. Now in case of Volhard's, what we are doing is, obviously halide ions are our analyte, but silver nitrate is added in excess and then remaining silver nitrate is titrated with thiocyanate ions. They are filled in burette. The next point of difference is our indicator. In case of Mohr's method, we are using chromate ions as our indicator. So potassium chromate is used as an indicator. In case of Volhard's method, ferric ions are used as an indicator. So ferric nitrate or ferric ammonium sulfate is used as an indicator. So these are the first 3 very obvious points of difference. Now the next difference in Mohr's and Volhard's is, this titration is carried out in, as you know, neutral to slightly basic pH, but Volhard's titration is carried out in acidic pH. So how we can actually achieve this? By addition of say sodium bicarbonate or borax, and this we can achieve by addition of free nitric acid. Now the next point of difference is We can carry out titrations of chlorides and bromides effectively, whereas in Volhard's method we can carry out the titration of chlorides, bromides, iodides and thiocyanates effectively. The next point of difference is in Mohr's method, the titration has to be carried out at room temperature, because as we increase the temperature, the solubility of silver chromate increases, and if it is a PPT, it is supposed to be less soluble, but if the solubility increases, it might lead to titration error. So reaction is carried out at room temperature. Similarly, in Volhard's, the reaction has to be carried in cool temperature less than 20 or less than 25, because the soluble complex which we are going to get at the end point, the ferric thiocyanate complex, it loses its color when the temperature increases. So in both cases, here we have to keep the temperature below 20 or 25 so that the color does not fade away, and here we have to keep the temperature at room temperature level, because the solubility of silver chromate is getting affected as the temperature is increased. I think we have covered all the points mostly. So now let's move on to the next method of endpoint detection, which is Fajan's method. So let's see it. Now let's discuss the Fajan's method of endpoint detection. So here also we will take the same example, sodium chloride as our analyte and silver nitrate as our titrant. Now Fajan's method is a direct way of titration, where we will be using eosin as our indicator. Now here the principle underlying this kind of endpoint detection is somewhat different. I will tell you. The reaction is same. So NaCl will react with AgNO3 silver nitrate to give AgCl PPT. Now what we are doing is we are making use of the property of the colloidal precipitate. Now what is the property of colloidal precipitate? As we talked in Volhard's method, when a colloidal precipitate is present in the solution of its own ions, it tends to adsorb the ions which are in excess. So imagine the condition, actually say this is the equivalence point. Before equivalence point, chloride ions are in excess because they are analyte ions, right? And after equivalence point, obviously silver ions will be in excess, which are of titrant ions, right? So what the silver chloride precipitate will do, before equivalence point, as the chloride ions are in excess, it will adsorb the chloride ions as the primary adsorption layer, and ultimately the silver ions will be adsorbed as the secondary adsorption layer. Now once the conditions move after equivalence point, what will happen is, now Ag plus means silver ions are in excess as we have seen, so it will comprise the primary adsorption layer, and now there is no chloride ions left because all the chloride ions are now in the form of precipitate. The negatively charged ions are nitrate ions, right? So nitrate ions actually should comprise the secondary adsorption layer, but there is presence of eosin. So this is the sodium salt of eosin and they are negatively charged. So instead of nitrate ions, the indicator ions will start to adsorb as a secondary adsorption layer. Now once they come in contact with the silver ions, which was the primary adsorption layer, the silver ions and indicator ions, they form a pink colored complex. They give the precipitate the pink color, and that pink color indicates the completion of reaction. So here we are taking in consideration the property of a colloidal PPT to adsorb its own ions which are in excess. Now here we have to consider a few points. The indicator which we are going to add should be oppositely charged to the one which will be adsorbed after equivalence point. So after equivalence point, titrate is going to be in excess. So Ag plus will comprise the primary adsorption layer. So indicator has to be negatively charged. So we are going to use that kind of indicators for this type of titration. Next, some factors affect the choice of indicators and altogether the endpoint detection by Fajan's method. First, what is the surface area of the precipitant? What is the intensity of color formed after the equivalence point? It actually governs the choice of indicator also. So these factors should be taken into consideration before choosing the right indicator for this type of titration. Another alternative theory is that once the charge on the adsorption layer, primary adsorption layer, shifts from negative to positive, there are some structural changes going on and that leads to the different color formation. But I think this theory is good enough to explain the color change, that the indicator and the primary adsorption layer, they give a different color, and then we can actually see that the color is changing, means the endpoint is reached. So this is how the Fajan's method works. It is called as adsorption indicator method. And now the last method is called Gay Lussac's method, but it is also called without indicator method. So we will briefly discuss about that also. So in Gay Lussac's method, what we are going to do is, we are not going to use any indicator, but we will actually make use of the process of precipitation, and ultimately it is resulting in turbidity. So we will call this method as turbidity method also. So what we will do in this, instead of a conical flask, we can use a reagent bottle which is stoppered. We will add sodium chloride, which is our analyte, and we will add silver nitrate, which is our titrant. So silver nitrate isn't added in excess. Say if we know that for 100 ml NaCl we are going to require 100 ml AgNO3. So we will first add 50-60 ml AgNO3 and then we will shake it. Also we will add some coagulant like potassium nitrate or barium nitrate. So the coagulant, once the precipitation is complete, the coagulant will settle it down. The precipitate will be settled down. So now I will go on adding the aliquots of titrant, say 10 ml, 10 ml, 10 ml. Now every time when I add silver nitrate in the bottle, I will close the bottle and I will shake the bottle. If the precipitation is taking place, it will result in turbidity, and after a few seconds that turbidity will be settled by the coagulant present inside. So the turbidity is showing, it means precipitation is going on, it means reaction is not yet complete. A point will come, see, after addition of 80-90 ml, I will reduce the volume of silver nitrate. So earlier I was adding 10 ml, 10 ml, 10 ml, now I will add 5 ml, 2 ml, 1 ml. And ultimately at one point I will realize that even after addition of silver nitrate, when I am shaking the bottle, turbidity is not getting formed, which means reaction is now complete. So that will give me a tentative reading, because accuracy is at stake in this kind of titration. See, we are not saying that the method is very accurate. Actually this method is obsolete. Currently it is not in practice much, but it is a method, we should know it. So in the next cycle I will take another reading, and at that time, before that tentative reading, say the tentative reading is 100 ml. So from 80 or 90 ml, I will add very little aliquots, say 1 ml, 0.5 ml, and then I will go on increasing the accuracy of endpoint in this method. So this is a method, Gay Lussac's method, without indicator method, turbidity method, whatever you say. Here we are not going to use any indicator, but we will be utilizing the tendency of precipitate to cause turbidity in the solution. So these are the 4 methods of endpoint detection in precipitation titrations. Let's briefly revise. The first one is Mohr's method, which is a direct method. Next, the Volhard's method, which is indirect or back method. Then the Fajan's method, which is adsorption indicator method, and the next one is without indicator method, the Gay Lussac's one. So I hope all of the concepts are conveyed properly and you are able to receive the concepts properly. You can go through the video one more time, and if any doubts, then you can ask in the comment section. I'll be happy to help. I hope this discussion was helpful. Let's meet in the next one. Till then, stay happy, stay tuned to Be Pharmawise. Bye.